Good afternoon, everyone. So the discussion I'll do now after Ronnie will be on a specific pressure management project, which was undertaken in Johannesburg. And sort of these are the topics that we'll cover. So Johannesburg Water sort of is an area that covers approximately 12,000 kilometers of pipes, 87 reservoirs, 33 water towers, approximately 700 PRVs or control valves, and approximately 300 PRV zones. And the project that we were involved with sort of basically focused on servicing all of those PRVs and ensuring that those PRV zones are discrete. And that the PRVs are set sort of as effective as possible in order to achieve water savings. So the ultimate goal was to achieve water savings, and the focus was PRVs and PRV zones. So Johannesburg is sort of known for having fairly high pressures. This is a photo from a newspaper in Johannesburg. Of the damage that occurred when there was a pipe break sort of in a specific area. So one can see there sort of, part of the wall sort of flew up and sort of landed on someone's car. So fairly high pressures they've got in Johannesburg. This is also a large mains burst in the CBD of Johannesburg. So again, sort of large pipe, sort of large pressure. The project sort of that we then did focused on where Johannesburg had PRVs and PRV zones to focus on setting those PRVs as effective as possible and ensuring that those PRV zones are discrete. So approximately 700 control valves and 300 pressure management zones. So obviously some zones had more than one pressure reducing valve. For each zone, we logged the pressure before and after the project so that we could assess if the project was successful and if the zone was discrete, and also to determine the water savings in each of these zones. And then Ronnie talked earlier about the pressure controllers. So in a few selected zones, we also installed smart pressure controllers where there was scope for additional water savings. So the project posed some interesting challenges. These are a few photos of some of the challenges we faced. So there was a PRV chamber where the roof was removed at some point sort of earlier, so residents used it as a swimming pool. Some of the PRV chambers were really dirty, so we had to first get a contractor in to clean all these PRV chambers before we could sort of work there. Some of the PRVs appeared to have never been serviced ever, so this was a PRV that was supplying a fairly smart neighborhood in the northern suburbs of Johannesburg. And they were probably unaware of how the valve looks like where their drinking water comes from. So we had to again get a contractor to clean this out and service the PRV. In some cases there were snakes. So in this specific PRV chamber, we got someone that handles snakes, and they carefully removed the snake and placed it in a safe area. And approximately a week thereafter, the data logger in this chamber was stolen. So we obviously realized that then that was the reason why the snake was there. It was the sort of protection sort of mechanism. Then focusing on the PRV servicing. So each of the PRVs that we serviced, we had to set optimal to try and achieve the maximum savings in that zone. Each of the PRVs were serviced, the strainers or the filters were cleaned. In selected cases where the PRV was beyond repair, the PRV or the isolating valve was replaced. And then photographs were taken of each step so that we can keep a record of all the work that was undertaken. So these are some of the photos of that work. So this is servicing of a small diameter PRV. There you're looking at the inside of an open PRV. It also involved larger diameter PRVs, and in this case, the isolating valves were replaced as part of the same exercise. Photographs were taken of all the parts replaced. So this is a sort of a valve seat, and one can see the damage on that seat. So this was obviously replaced with a new valve seat. The pilot valves and the fittings that's part of the control circuit, that gets photographed so we can have a record of what was on the PRV before and after the servicing. The strainers were cleaned. So this is a strainer where you can see it's almost completely blocked with dirt and rubble. So each of the strainers were then cleaned as part of the same exercise. As mentioned before, so in each of these zones where we serviced the PRVs, we logged the pressure before and after, and if there was a water meter, also we logged the flow. And that was, the pressure logging was basically used to inform us if the PRV is at its optimal setting, and also to pick up if there's any problems with a boundary that's not discrete, or any other problem in the zone. So the pressure logging results, this is an example of how it looked like. The left-hand part of the graph is basically before the PRV was serviced, and the right-hand part is after the PRV was serviced. One can see the sort of the purple and the green line is the outlet pressure of the PRV, and the red line is the upstream pressure. So everything downstream of the PRV was stable after it was serviced. The benefit that we found from using a web-based system was that both the teams that sort of were based in the field, together with the project manager, together with the client, could monitor the logging data as we moved from zone to zone. So there was a great benefit of having the data on a web platform where everyone could log in and see the same data and then comment on that. So this is another example. The left-hand part of the graph, one can see that the lines are following each other closely. So in this case, the PRV was fully open, so there was no difference between the inlet and the outlet pressure. And the right-hand side of the graph, one can see that the PRV was serviced, and obviously one can see the difference between the inlet, which is the red pressure, and the outlet pressure, which is the blue pressure. So Ronnie touched earlier on the importance of zone boundary valves. So this is just a 2-3 slides to explain the importance of that and how relevant that is to pressure management. So on the screen, one can see basically two zones, an upper zone and a bottom zone. And the two zones are basically separated by one closed boundary valve, which is marked in black, a pressure reducing valve, which is in the middle where it says MZ, and an open boundary valve, which is marked in white. So with the current situation, what will happen is the water will run down from the reservoir, and it will not go through the PRV, it will go through the open boundary valve. So instead of the pressure being reduced for the bottom zone, all the water will run through the open boundary valve, and one will get very high water pressure at the bottom of the lower zone. So in order to ensure that the water runs through the pressure reducing valve, you have to close that second boundary valve. And now all the water is forced to run through the pressure reducing valve. And one can see that the pressure now at the bottom of the lower zone is lower than it was previously, because now the water is running through the PRV and not through the open boundary valve. So as Ronnie mentioned earlier, to keep those boundary valves closed is a very important factor sort of in pressure management. This graph basically shows what will happen if one of those boundary valves are open. And one can see that the blue line is the flow, and there in the middle of the graph, the flow at night started reducing to 0, and there was a slight increase in the PRV downstream pressure, which is that pink purple line. So what it means is someone opened the boundary valve, and the flow was no longer going through the PRV, it was coming in through the boundary valve sort of at night. So if you log the pressure and the flow permanently in the PRV zone, you can pick this type of problem up much quicker than if you had no logging result. So the next topic I'll raise, I'm good, thanks. The next topic I'll raise is, because we serviced so many PRVs and there were so many PRV zones, there was quite a big data set. So for 700 PRVs, all the parts that were replaced, the logging data, etc., it was quite a large set of data. So basically, to manage that, we created a database that I call PresBase here, and this was also a web-based database. And in this database, we basically kept track of each part that was replaced, each logging data, each photo that was taken. So basically a record of all data on the project. So we are then able to filter this data and to, for instance, see how many 150 diameter diaphragms were replaced, or how many pilot valves were serviced. We also further added some features to this database, so that we can do automatic reporting from the database. So because we already captured all the data into this database, we programmed the database to automatically prepare reports for us. So this is an example of an operation and maintenance manual. So the data in the database was used, and we basically punched a button, and then you create an operation and maintenance manual for that zone that can then be used by the operations team when they do maintenance on the zone and on the PRVs. So the results, what we got, there was a reduction in leakage. We'll show that a bit later. There was a reduction in the number of burst pipes. And then we also found that as we were going from zone to zone and investigating the PRVs, we picked up the number of differences between what the GIS drawing showed and what we found on site. And those differences were then given through to Johannesburg to update their GIS. So this is a flow logging result for one of the zones, and the left-hand side of the graph shows the flow before the project was implemented. So the night flow was 132 cubic meters per hour, and then the right-hand side of the graph shows the flow and pressure after PRV was serviced, and one can see that the night flow was dropped from 132 to 90 cubic meters per hour. So in similar, we've got results for other areas. This was a low income area, a fairly large area, and here the night flow dropped from almost 1,000 to 680 cubic meters per hour. So in each zone, sort of where possible, we monitored the savings so that we in the end can calculate the sort of the total savings for the project. We also gathered the pipe burst data before the project and after the project. The text is a bit small, but basically on the left-hand side of the graph is the monthly pipe burst for a specific zone before the project, and on the right-hand side of the graph are the pipe burst for that same zone after the project. And in this case, the monthly pipe burst dropped from 16 to 6 after the PRV was set and the zone was made discrete. Another graph showing the reduction in burst pipes. And in this zone, the burst pipes reduced from 20 per month to about 8 per month. So both a reduction in leakage and a reduction in burst pipes were some of the benefits that came from this project. The total reduction in burst pipes, it reduced from approximately 36,000 to about 32,000 sort of burst per annum, sort of in the period before sort of to after the project. So it shows there is, even after the project, there is still a significant number of burst pipes in Johannesburg. And that would partly be due to there are still a number of areas in Johannesburg that's not yet under pressure control. So those PRVs would still need to be installed in future. And partly some of the networks in Johannesburg is quite old, so those networks would need to be replaced. But the graph does show that there was at least sort of a positive impact in the sort of the reduction of burst pipes. So in summary, we inspected approximately 764 control valves, and we serviced about 523 of those. Some PRVs we could not service because for reasons, for instance, we could not shut the water off because the isolating valves were not working, or there was a certain problem in the zone, or there was a new project that first had to be implemented. So hopefully those remaining PRVs will be serviced by Johannesburg at some stage. We cleaned 260 strainers about, and we confirmed 267 zones as discrete. So these are sort of significant numbers, and all of that resulted in water savings of approximately 12.7 million cubic meters per annum. So at 10 Rand per kiloliter, which is approximately the Rand water cost at this stage, that in Rand terms, the savings would be approximately 127 million Rands per annum, or just under 7 million US per annum. The total cost of the project was approximately 25-30 million. So one can see with that savings that there's a fairly quick payback with pressure reduction. And then burst pipes, as we said, reduced from approximately 36 to 32,000 per annum. So some of the lessons that we've learned is, as Ronnie also mentioned earlier, that significant water savings can be achieved through pressure management. And pressure management can be used either in areas that are sort of flat, or where the topography sort of is rolling. I think the best would be to design the pressure management solution to a specific network. So one solution is not going to work for all networks, but certainly if each network is analyzed, one can determine the best pressure management solution for that specific network. For all PRV zones, we recommend to permanently log the pressures and, if possible, also the flows. we showed some graphs earlier that the logging data on our project was displayed on a web-based system that we call Zednet, but the Johannesburg project did not involve installing permanent loggers. So the downside of that is after the project, there was no control to determine which of those zones were breached or where did the PRV stop working. So as a long-term solution, we recommend to log pressures and flows permanently and to display the data on a web-based system. That will then assist the teams working on the PRVs as well as the managers to keep track of their zones and also of the PRVs. Ronnie mentioned the challenge of zone boundary valves earlier. So where possible, we would say to minimize the use of boundary valves, and where a boundary valve is specifically required, try and mark the valve and try and lock it, and so that there's some sort of a control over when that valve is open or closed. The web-based platform that we use to keep track of all the data and the work undertaken was quite useful, and we saw that it saved a significant time to generate a report for all those zones. It was quite beneficial to have that all in one single database. The smart controllers, as we've discussed, if the additional water savings that you can generate from installing a pressure controller outweighs the cost and the additional maintenance, then we would recommend to consider a controller. But if the additional water savings that you're going to get from a controller is not going to be notable, we would recommend to stick with a fixed PRV that you set on a fixed setting with a data logger that then can keep track if that PRV is working correctly. And then a last note is that if you try and log your PRV chambers to keep the equipment safe, like the brass pilots, etc., or else use snakes. Right, I'll end off with this slide. Thank you, everyone.